Hi everyone, I'm Lingpeng Chen. In this video, I'm going to share with you my research topic, Distributed Target Estimation and Ergodic Control for Multi-Robot Informative Path Planning. To start with, let's consider tasks like monitoring wildfires or tracking animal herds. These tasks involve gathering vast amounts of dynamic information and are essential in the real world. They are challenging and costly for us humans due to the scale and complexity. So in our project, we are tackling the challenge of using drones to gather information from multiple ships in a vast ocean. But there is a problem that the camera sensing range of our UAV is limited. Once a ship sails out of sight, our knowledge of its status decreases. So we need a smart strategy for drones to regularly return to the ships and update understanding. So far, most research in the informative path planning has centered on a single robot. However, developing multiple robots simultaneously could enhance the efficiency of gathering information. Therefore, our project aims to optimize the paths of multiple robots. Think about a 2D ocean environment you want to keep an eye on. Now, we have drones flying over it. We split this environment into the binary cell, each assigned to a drone. It's like giving each robot a neighborhood to watch over. Each robot is accountable for the region closest to it, and each robot will use its own data to predict the information distribution of the target in its own area. Let's regard our ship distribution as a occupancy grid map M, where in each grid there is a number represents the number of targets in that region. Now, our robotics, all similar and equipped with a certain field of view camera, they can only see targets within its field of view, and their sensing quality drops as they move far away from the targets. Therefore, we measure the value of the information the robot collected by considering both the robot sensing performance and target distribution. Intuitively, a robot gathers more information as it moves closer to the target dense area, improving its observation and coverage. And by computing information value at each location of the map, we create an information distribution map. Now, let's get to our main objective, the informative path planning. Our goal is to plan a path, the P star, for the UAV system so that our robots can go to the high information areas and maximize the information gain I. We estimate the information gain throughout the mission by multiplying the information value by the uncertainty of the robot estimation. This is because as we observe an area over time and gather sufficient samples, with the increase of the certainty, the information gain decreases. At this point, it is crucial to explore new areas with high uncertainty, seeking for the new high information regions and observe new targets. Before getting into our approach, let's talk about our simulation environment and ship movement dataset. They are crucial for designing our algorithm since they capture the real-world ship dynamics. In our simulation, we have two types of vessels, fishing boats and pleasure boats. Each has a different purpose and thus unique sailing trajectories. They travel between different target points, like points of interest at sea and the dock, with PS and PE being the start points and the end points. We model the trajectory between the pairs of target points using a third-order desire curve, which help us to calculate the ship positions at various times along its path. The middle point, PC, is a control point controlling the path curvature, which is influenced both by the wind and wave velocities. This method generates a spatial-temporal dataset of ship movements. For the rest of the discussion, we are focusing on the path planning in a static spatial environment, using a single frame from our dataset. And our immediate future work will tackle planning on the spatial-temporal dataset. Then, let's talk about our informative path planning method, a fusion of the Mixture Gaussian Process and Ergodic control. To start with, a trajectory is ergodic with respect to an information distribution at the time that the robot spent in a region is proportional to the amount of information in that region. So here is a ergodic matrix where Ck is the Fourier coefficient of the trajectory statistic distribution and phi k is the coefficient for the information distribution. So what the ergodic control algorithm do is to find an optimal controller that output the trajectory so that the two distributions can be as close to each other and such that the ergodic matrix can be minimized. As you can see in this video, with the knowledge of the ground truth information distribution, this single robot are able to not only spend the majority of the time searching for the high information areas, but also visiting all locations in search space for new information, which enables the robot to plan a path for collecting informative samples. But the problem is how to get the information estimation. So our answer is the Gaussian process, or GP in short. GP is a non-parametric regression method, which is popular for its ability to model spatial phenomena while giving the uncertainties. To better represent the information distribution, we use the Mixture Gaussian process, which offers us a better modeling capabilities. In this case, xig, yig are the sample set and the ground truth values are best described by the ig's GP component, and the mixing probabilities are determined through a distributed EM procedure. Overall, the whole structure of the algorithms are as follows. At the start, each robot gets a bit of preliminary information, which typically gets from the satellite image. We randomly place our robot across the map and update their zones of responsibility, or vulnerable cells. Each robot trains its own mixture GP model using its local data, and the model predicts the mean and variance over its own vulnerable cell. Then, based on the predicted environmental information, which is the predicted mean value, and also based on the robot trajectories, each robot uses the ergodic controller to help the robot plan a route with a certain number of set points within its vulnerable cell. And after the robot follows its path and collected samples, they will decide if they need to update their zones or the vulnerable cells according to their current position based on the frequency we set for updating these vulnerable cells. Then, in the next round, we will use these new samples with our mixture GP to get a new estimation of the information distribution, and then we will do it all over again. Finally, we will evaluate our approach on our artificially designed shape dataset. For comparative reason, the initial location of 3 zones are set with the same location on the map, which are on the borders and corners. Each robot is represented by a different color circle. We split the map into the vulnerable cell based on the robot location, which is marked by the red dashed line. Using some limited prior knowledge, we estimated the information distribution using the mixture GP. In the image, the brighter the color is, the higher the estimated information value is. The second figure shows the path that our robots take, with each colored trajectory representing a different robot trajectory. You can see that the robot has covered all the high information areas, and from the winding path, we can notice that the robot has spent a lot of time in these high information regions. While in the low information areas, the robot trajectories are straighter, showing that they didn't stay long. And the right figure compares the zone's estimated information distribution with the actual ground truth one. By this point, the Jones has output a pretty accurate estimation of the whole distribution. This shows that our algorithm really does work. In addition to that, we looked at both the information gain and the total cumulative information gain of the UAV system. You can see that the amount of information gain changed at each iteration. Interestingly, it hit at a peak at around 4th round, and then quickly dropped. This suggests that the drones move away from the high information areas to search into the other regions. And after a few rounds, the curve hit another peak of the information gain again, which tells us that after some searching, the drones find another high information area and started to observing the target there up close. In addition, we noticed that how often we update the vulnerability cells greatly affects the algorithm effectiveness. The vulnerability cell updates has been an area in need of more research. From our experiments, we found that updating vulnerability cells every 3 rounds leads to the highest information gain and a reasonably low estimation error, which gave us some good results. And we will take this knowledge and continue investigating this area in the future. In conclusion, our research presents a new active learning framework for spatial environment that tackles informative path planning for multi-robot systems. We devised an information distribution map for the path planning, which takes into consideration the target locations and robot sensing capabilities. We combine this with a mixture GP for estimation and ergodic control for gathering informative samples. Moreover, we built a ship tracking simulator with 3 VTOLs, which will help us to prove our approach in the future on our specially designed ship dataset. Looking ahead, we could expand our algorithm to the spatial-temporal models and improve the inter-robot communication method to better handle the real-world challenges in the informative path planning. Finally, I want to acknowledge that this work was supported by the Carnegie Mellon University RACE program, Shenzhen Institute of Ears, and the CUHA Shenzhen. We are grateful to Dr. Dolan and Rachel for organizing this program, and I would like to thank my mentor Shiva, Dr. Luo, and Dr. Sakara for their insightful guidance. That's my presentation. Thanks for watching this video.